All right. So far, what we learned was that we could that on the top of on the top of on the top of say usual basic cell of recurrent neural network, there have been many optimizations. The most popular ones are LSTM and followed by the people connections on LSTM and then GRUCell. All right. So GRUCell and LSTM was designed to keep the short-term and long-term memory, while GRUCell basically keeps only one kind of memory as carryover. And for most of the cases, the GRUCell works fine. Okay. For most of the cases, GRUCell works fine. And if you want more sophisticated one, then you can use the LSTM. Also, LSTM has been used and has been proven more as compared to GRUCell. Specifically, when it comes to say language translation, then the LSTM is the one that is used. All right. So far what we have learned is the various architectures of the RNN and various architectures of the individual cell. Great. So there are many use cases of RNN. Some of them are say natural language processing and translation and there are, and you will see more use cases. So one of the most popular use case of the recurrent neural network is natural language processing. So most of the state of the art and NLP applications such as machine learning, automatic summarization, parsing, sentiment analysis, and many more are now based on RNN. And so we'll take a look at what a machine learning translation model looks like. This topic is very well covered by TensorFlow's awesome word-to-vec as well as sequence-to-sequence tutorials. Sequence-to-sequence tutorials is far more deeper, as well as word-to-vec is far more deeper. These are kind of both of these are themselves kind of uh, um, 3 months projects. Okay, specifically the sequence to sequence tutorial, they are actually quite deeper and it would require a separate maybe a couple of sessions to just deep dive into each of them. And so that we will not go into too much of details on either one, but you will get the fair bit of idea that how does sequence to sequence and word to vec work. All right. So so we'll do the basic treatment and we will get the fair bit of idea of both of these. All right. Now, before we start, let's answer this important question. How do we represent a word? Right? Let's say um, let's say there's a word called word, W-O-R-D. Word is not just, or let's say there's a word called person. Just give me a second. There's a message. All right. So a word, let's say a person. How do we represent it to the computer? If it is just person, just the ASCII values of the various characters, that's not good enough. That's not good enough. That does not convey the meaning of person. All right. So so now let's say here a question from Binta is, could you give us some sample codes or reference of NLP application? NLP applications are these of, there are many NLP. NLP represents natural language processing, and whether it's a speech synthesis, meaning converting the voice into converting the text into voice, or it's voice recognition, meaning converting the voice into text. In both of those, the along with let's say a chatbot. So actually the sequence to sequence is very much used in creating the underlying API for chatbot, creating creating understanding the human language. And there are many more applications of NLP. So one of the things that we were doing is we worked with this hotel called Tribo Hotel. So they wanted to uh, extract information from the email and automatically book the hotel if the or uh, extract like booking times and so on from the user's email. User would generally send an email in a free-flowing text that please book hotels for this person, and the person's name and everything is in tabular format. So those point of time to extract information from text, to understand text, is the uh, purpose of natural language processes. Also translating one language into another, that's again a use case of NLP. So sequence to sequence that we talk about here is essentially used in translating one language into another. The Google Translate is the translate.google.com is now based on sequence to sequence. This change has occurred in last 1 year. They have been working on it for like 3-4 years, and in a recent past they moved translate.google.com from the traditional statistics based translate engine to sequence to sequence or deep learning based engine. All right, so yes, there are projects based on NLP in this. So it's not NPL, it's NLP, Vinta, and natural language processing. And yes, there will be projects on NLP. So we'll be putting a couple of more projects into this. All right, now let me ask you some more questions. There are many more applications of natural language processing. One of them, the most frequent one, is sentiment analysis, detecting sarcasm, or uh, and and like correcting grammar, auto completing a sentence, that again comes as part of the NLP, and you will learn that very soon. So whatever we have learned so far, we learned how to process an image by what did we understand how do we process the image. We process the image using, say, a network like convolution network, whereby we break the image into tiles or overlapping tiles, and then we process individual tiles and we feed that to the neural network, right? In the similar way, can we do the similar thing with a word, with the text, right? So question is, how do we represent word? That was the hardest question. And the first thing was, let me ask you this. Here, say we had to handle climate. You remember our one of the projects that we did, end-to-end project, whereby there was one of the variables called categorical variables. Now, how do we generally handle categorical variables? Anybody? So, so how did we handle categorical variables earlier? Like climate here. Correct. Using encoding such as one hot encoding, right? So here now let's take a look at it. So had had a column been a categorical variable such as climate, we could have converted into one hot encoding. Is it clear what we did? We basically took the column climate and converted that column into two columns, climate underscore cold, climate underscore hot, and and the cold is essentially here we're putting a flag 1 in case of cold, and in case of hot we're putting. All right. So the important part is that can we do the same thing with the comments? Is it clear what we did with the climate column? Because we need to convert the text into some numbers, because all, whether we talked about linear regression, talked about decision trees, talked about neural network, where we are multiplying weights by weights into instance um, instance features, we basically multiply weights with the instance features and so on in neural network. So we need to convert all the features of the data set into numbers, right? So climate we were able to convert by breaking it into multiple columns, right? Now, question is, what about comments? How do we convert this column called comments into a number? Ross suggests that need to split up sentence into parts and encode. All right, very good. Any other suggestions? Okay. So we were able to convert the climate column into numbers by hot encoding it, by taking all the values, unique values in the column, and putting it into the multiple columns. So any suggestions for comments? Right. One of the suggestions that come again and again is we take the we take the we take the data from each column and create the word counts from that column. Okay, word count is further enhanced into something called TF IDF format, in which we remove the most common words. So we can convert this into a huge dictionary of words where we list down the counts of each word in that column, right? So so one option could be to represent each word using a one hot vector. But consider this: suppose you have a vocabulary of 50,000 words, then the nth word could be represented with 50,000 dimensions, right? So if we did what we did with climate, like we converted one into two columns because there were two values, hot and cold, right? In case of words, there are 50,000 words, let's say, in a dictionary. So do we have a vector having 50,000 dimensions? With such a large vocabulary, the sparse representation could not be sufficient at all, right? Also, even if we do the word count, as in we count the words and so on, that could be a minor relief, or could be better than not having it at all. But still, we would not get to know anything about our data, anything about a sentence. Ideally, we want, say, similar words to have similar representations. If, let's say, um, the representation for say frog and a toad, the two words, though the two words like frog and a toad, those are extremely different and very different from each other, but still we would want their representations to be similar. Okay, so that when we, like, if there are two instances in our data set, in our usual data set, if we subtract them, the values should be very small, right? They should be very closer to each other. So we would want, as part of NLP, the heart of NLP is all about figuring out the meaning of word, such that the meaning could be a list of number. Meaning does not have to be something that means something to humans like us. So meaning is the meaning is something which is like based on vector algebra. So we should have each word represented as a vector of values, such that when you subtract the two vectors, they should be, the difference should be very small if there are words are similar. So we would want the similar words to have similar representation, making it easy for the model to generalize what it learns about a word to all similar words. For example, if the model is told that I drink milk is a valid sentence, and if it knows that milk is very close to water but far from shoes, then it will know that I drink water is probably a valid sentence as well, while I drink shoes probably is not. Syntactically, grammatically, I drink shoes is a valid sentence from the grammar perspective, but from the reality perspective, it is not. So using NLP, if we are able to represent similar words to have similar representations, we could give warning to the end user that, hey, I drink shoes does not make sense to me. Okay, so how can we come up with such meaningful representations? The most common solution to represent each word in the vocabulary is using a fairly small and dense vector, 150 dimension, called embedding. So the most common way is to take a word and represent it as a dense vector of 150 dimensions, or say 200 dimensions, and these are called word embeddings. Word embedding is a common industry term. Whenever we want to say that, hey, I'm doing NLP, so the first thing that comes is that which word embedding are you using? All right. So and we just we just let the neural network learn a good embedding for each word during training. Now question is where do these word embedding come from? Let's say let's say word embedding means that we're converting king into list of numbers, man into a list of numbers, and woman into list of numbers. There are many word embedding. Before I proceed further, let me just tell you that there are many word embeddings available, such as glove, and you can also try Jansim, or we call it word to vec. Okay, so these are the word embedding available to us. So what are these word embeddings? Word embedding is basically a huge corpus of you can say, okay, so word embedding is nothing but it if you load and exist, somebody else has created word embedding already, say glob vectors or Gensim, they have already created word embeddings for all of the words, and it's a huge data. So you just ask the word embedding that give me give me the vector representation of each of these words. So it'll give us a list of numbers for each word. Like for example, we can do a lot of magic with the word embedding. For example, king minus men plus woman actually gives out queen. Okay, actually gives out queen. So this is what it means. This is basically something that has been done in last couple of years, and this has been super successful way of representing a word. All right, so it essentially, let me show you the code. For example, here I'll just walk you through the code, although it may not work because our servers are not allowing this data to be loaded. So if you want, you can experiment with this. So Google News Vector, you can just download it from their servers and try to load it using local machine if it is not working on CloudxLab. So you could try that. So here you need to import GenSim model. So you were saying you have to also install GenSim. GenSim is a library which has implemented Word2Vec. Word2Vec is an algorithm from Google, which basically uh, details out how to convert a word into embedding. Okay, we're going to talk about what does these numbers mean. So before that, I'd like to show you this part. So here we are saying that from GenSim models, import keyed vectors, and then we are loading this binary data. This binary data or embedding has been derived from Google News, Google News, and this file is around 3 GB. Okay, so here we are saying that load this vectors. These are predefined list of words having the vector representation of all of the words. So here we are saying that load this file, okay, and then we are asking the model that can you give me the most similar values to these to the resulting value. Okay, we are saying positive woman plus woman and king, and negative man, which is equal to take the vector as in the list. Woman will be represented as a vector, right? Vector of 300 values here, and king will be represented as another 300 values vector. And we are saying woman plus king, meaning add this vector to another vector. So woman will be represented as this kind of a vector, 300 such values. Similarly, king will be represented with similar value, and so on. So then you will see that the answer will be queen, and this will be the uh, probability of that. Okay, so essentially the point I was trying to make is that once we are able to represent the word in the embeddings, if we are able to load or find out the embeddings of each word either using Word2Vec or using Glob, we shall be able to do rest of the machine learning as usual. We could apply neural network, we could apply all kinds of algorithms that we have learned so far. All right, is it clear? What does it mean by embedding? How embedding is derived, that we learn after this. How to convert a particular word into the embedding. That's what we will discuss now. Not clear? Is this idea clear? Okay. All right. All right. So yes, here essentially each word is like, here we are representing king in a three-dimensional vector. It is like three values. representing king, three values representing queen. Just we are trying to for the display purposes. So we are saying what king is to queen, man is to woman. Similarly, walking is to walked, and swimming is to swam. Okay, if we have the vectors representing the word, we should be able to do this. All right. So this is essentially what it means by word embedding. All right. Now, so there are two ways to derive the embedding. How did we come up with embedding? Okay. Okay. So all right. So if the meaning of word embedding is clear, then I'll move ahead. Okay. Converting each word into this kind of the numerical representation of a word is what it means by embedding. All right. Now, how do we come up with, how did we calculate these embedding? So they were basically the whole word embedding philosophy, or vector space models we call them. The vector space model or the word embedding is based on this hypothesis that words that appear in the same context share same meaning. Okay, so the words that are surrounded by similar words. So if um, uh, I drink water and I drink milk. If the word milk has been occurring again and again with drink, as well as the water is occurring again and again with drink, therefore water and milk are very similar. Okay, so if let's say, okay, let me just share the slides are same as yesterday. Okay, yeah, there have been some changes, but all right. So let me see if I could just draw. All right, so let's say I like water. I like, or say I drink water, and I drink milk, and I swim in water. Okay, all right. So here the uh, okay, okay, and all right, let's just, okay. So like this. So here what we see is that the word water has been occurring with very frequently with drink. So as well as the word milk has been occurring very much frequently with the drink. So if we do a frequency analysis of the context, like what are the words that occur with the similar frequency after drink, what are the words that are suggested after the drink, therefore those are the words which are similar to each other. So if we start writing saying I drink, and then it can give a suggestion that it's water, milk, or beer, right? So that's the kind of suggestion that you could get, the one that Google shows. So Using those kind of mechanism, but by finding the context, like what are the words that occur in the same context. Based on that, we could design the word embedding. We could design the word embedding. All right. Now, this is basically what we call context. So not only the left, but can also do it on the right. Okay. Say, uh, all right. Okay. And so here, for example, the now the word drink is followed by water as well as take is followed by water. Therefore, drink and take are similar in nature. Okay, so based on the frequencies of the words occurring in the context, we come up with embedding. All right, so there are essentially two approaches. One is count-based methods. We call them latent semantic analytics. Count-based methods, as in we count the words and we do the frequency analysis based on the count of the words. Okay, we take a sentence, we break it down into counts and so on, as well as how many words occurred after a particular phrase, how many words occurred before the particular one. So those are count-based methods that based on the number of counts, but there are more sophisticated models such as predictive methods. The one that we are going to do today is the second one, using neural network to figure out the meaning of words. Using neural network and a huge corpus of text, we can figure out these meaning of words. Okay, so we could keep on feeding to our RNN. I drink water, and then followed by the next word, and so on. So that way, it will learn to predict or suggest the next word, and it will also learn the embedding. Okay, that's the predictive method that we will be using neural network, and doing the probabilistic language model, we will be able to create the embedding by ourselves. All right. So ideally, in the real cases, in the practical cases, most of the time, all you will be doing is use any of the embedding technique. Okay, use any of the existing embedding techniques, and then then um, just convert the input data into the vectors and then apply the algorithm. This is something that you will do most frequently, but sometimes you might have to come up with your own embedding. Why? Let's say you are handling the text corresponding to a separate domain, a small vertical. There you would like to create your own embedding, as in your own vectors which are more specific to your use case. Say, for example, you're doing the analysis of law related documents, and you would like to enhance the embedding by augmenting it with your own data statistics or your own corpus of text. In that case, you will be building your own embedding. Okay, so one approach was count based, in which we counted the frequency of words. The other one is neural network based. Count based were something like compute the statistics of how often some word co-occurs with its neighbors in the large text corpus, map these count statistics down to a small dense vector for each of the words. That was count-based methods, or we call them latent semantic analysis, lib. All right. So all we do is we just count how often the word coexists with others, and based on that, base and convert these count statistics to some vector. Okay. Now, the second one is the predictive models. Predictive models is we try to directly predict a word from its neighbors in terms of in terms of learned, small, dense embedding vectors. Consider parameters of the model. So what we're going to do is we're going to the way we figure out weights, in the same way we are going to figure out these embeddings uh, from the model. All right. So so word2vec So word2vec is one such computationally efficient predictive model for learning word embeddings from raw text. So again, embedding is a general term, meaning or vector space model is a general term saying the method to converting one string into numbers is called the so there are two approaches for word embedding. One is count based and predictive. So this is general word. And predictive models are basically based on a particular paper by Google on Word2Vec. And Word2Vec is, as of today, Word2Vec is kind of a standard term. All right. So the predictive models directly try to predict a word from its neighbors in terms of learned, small, dense embedding vectors. It comes in two formats. One is continuous bag of word model and other is skipgram model. So continuous bag of word is predict the target word from the source context, like the car sits on the mat. And skipgram model is the reverse. It predicts source context words from the targeted words. Okay, so it treats the context target pair as a new observation and tends to do better when we have large data set. Okay, so these are the various models. Just to summarize this, we will be using the skipgram model out of the word2vec. Okay, all right. So let me describe this. So what we're going to do is we are going to predict. One way was that we assume. Okay, let me take a step back. So what we are going to do is we're going to predict the word's embedding based on the context in which it occurs. Okay, now that's the CBOW, that's the continuous bag of words. We we break it down into we keep on breaking down the sentence into the parts. Now the second way is second way is the skipgram model, and it's actually these are very two similar mm, two similar models, and we will see the difference a bit later. So skipgram model is something that scales very well when the data is really huge. Okay, now so all right, let me describe this. So both the models, the word2vec models, are traditionally trained using the maximum likelihood principle to maximize the probability of the next word given the previous history of words. Okay, in terms of softmax function. So what we are saying is that the way we trained our models was to maximize the probability of next word. Okay, given the previous H word. So what we always did was we came up with the word embedding for each word such that the next word, the probability of the next word is highest. We basically fine-tuned the weights or the word embeddings such that the probability of the next word is highest given previous words. So this is how it looked like. So the score of the H given WT was highest, right? That is the probability that we needed to compute. The only downside of this one was we had to do this for every word in the vocabulary. So what? So the way this model was that we will given say a sentence like the cat sits on the mat, right? The cat sits on the, right? We come up with the next word such that the next word has the maximum likelihood. And how do we do that? We pick every word in the dictionary and then we try to fit in there and see what is the probability, how many times particular word has come after the cat sits on the mat. The cat sits on the, how many times it has come. So we pick every word in the vocabulary, compute the score, compute the score or probability of that word coming after this phrase. We try all possible words and compute their probabilities, and we sum up those all probability. That becomes the score in the below. Basically, this is what we did as part of softmax, that we computed e to the power of all of the values and then we divided by the correct one. So this is the right one and these are the all values. Now you can see that if there are 50,000 words in the vocabulary, we will end up with this score computation at least 50,000 times, then doing the summation and so on. So this model wasn't right. This model wasn't right. Instead, what was done was, instead of this mechanism, we know the correct word, we pick its probability, okay, and we compare that with any random word, any random other words, assuming that all other random words are going to have lesser probability than this word. And using that mechanism, we generally trained it. Okay, so this is the model it was earlier, that if we have to do this, we will try to fit every word from the dictionary. We'll say whether W1 is fitting, W2 is fitting, W3 is fitting, W4 is fitting, and so on till the end after this, and we compute the probability of these ones, and that was the standard model. This one was very expensive because we needed to compute and maximize, normalize the probability over the whole of dictionary. Okay. A question from Minta is how to obtain the value of H. So each sentence in the whole text, will become the context history. First, we will try with the cat, then the cat sits, the cat on, and so on. So the whole context or the whole history, this is going to be done for all of such phrases or such sentences from the text. All right. So right, so we keep on coming up with these probabilities here. We keep on trying to fit it here and then see which word is most suitable here, right? So this method was extremely expensive. Therefore, the other method, comparing this with some keywords, we pick up, instead of comparing with every word, what we compare our actual word is with the random probability, random words. So the number of words exclude the target. Right, right. So that's right. In this case, what we are going to do is, in this model, we we have to choose the embedding such that the mat, the actual word mat, should have the higher probability of fitting it here. Okay, higher probability of fitting it here as compared to random words. We are assuming that the random words we are picking are noise. Okay, and of course that that is wrong, because not every word of these is a noise. But since we are statistically picking random words, therefore the chances of them being wrong is very high. So we keep adjusting the values of the the numeric representation of this one such that the the probability of this word, the right word, is highest here. So what we are going to do, what we do is, instead we train models using a binary classification objective like logistic regression to discriminate the real words, the words that fit in here, versus the k imaginary words w in the same context. All right. So computing the loss function now only scale with number of noise words that we select, not on the. So since we are not comparing all of the words, instead we are just comparing the k words, or you can say k noise. Therefore, this makes it really faster. So all we have to do is we have to come up with some loss function that represents the loss, as in it's not fitting here. So we have to represent mat with numeric values such that this this fits after the context. All right, and that's where the non-contrastive estimation loss comes into play. Okay, so the way the way we figure out the embedding is, first of all, we so there were two mechanisms here. One was taking the actual content, and breaking it down into context followed by the word. For example, the brown, as in, instead of only creating context based on the word that was before a word, we take both of them. So quick, the and brown is the context. So quick is followed by brown, and quick follows the. So we will basically create these kind of tuples. Okay. So what we are saying is, after this context, in this context, generally quick comes. In this context, generally brown comes. In this context, generally fox comes. Okay. All those words who have the similar contexts are going to have similar embedding. All right. So that's what is the scriptgram. Now, this was the first technique. Now there was further enhancement to that technique called with skipgram. It inverted the context. It said that the task becomes to predict the and quick based on the and brown from the quick. Okay. Given quick, we have to predict what will come before it and after it, instead of trying to predict quick. That was skipgram's model, in which it was slightly inverted model, in which we were trying to guess the context from the word. We were trying to guess the context from the words. So we would choose the embedding such that we are able to guess the context, and we are able to pick the context correctly. All right. So what we are going to do is, at every training step T, for the first case above, the goal is to predict the from quick, okay, as well as the from quick, and quick from brown, and so on, or brown from quick, and so on. So we have to come up with this kind of model whereby the goal will be to predict the context from the word. So we select some noise, we select some random words by drawing some random words from entire one, try to fit that word in the context, okay, and see how well it is fitting. Okay, so for simplicity, let's say the number of noise, the data that we are picking is 1, and we select sheep as noise example. Next, we compare the loss for this pair of observed and the noise. So here, this is the loss function. So don't worry, even if you don't get it. So don't worry, it's not mandatory to know this part. Okay, so here all we are saying is this is our loss function. We are summing up the probabilities of the following quick as well as sheep, okay, sheep following quick, okay. So or sorry, so quick following the quick in the context of the as well as quick in the context of sheep, right? So we basically compute this probability, and this is the function that we try to minimize. Okay, so the goal is to make an update to an embedding parameter. So we will initially, just like we did in our neural network, we assumed certain values of weight. In the similar way, we will assume certain values of embedding parameters, and the goal will be to change or tweak those embedding parameters or the word embeddings to improve the objective function. The objective function is that our word should fit the context. The word should fit the context. So that is the objective function. We do this by deriving the gradient of loss with respect to embedding parameters, right? Just like the way we did we did derive the weights. Okay, so we are going to exactly use the backpropagation for optimizing the embedding parameters, okay, or word embeddings. So each value of word embedding, that's a large vector of numbers, is also called embedding parameters. So just like in case of our usual neural network, we have a loss function. We have a loss function. We tweak this loss function in order to sorry, we don't tweak the loss function. We minimize the loss by tweaking the weights. And how do we tweak the weights? By using the backpropagation, by using the gradient descent. We tweak the embedding parameters here as we tweak the weights in the usual neural network. All right. And we then perform an update to the embedding by taking a small step in the direction of gradient. When this process is repeated over the entire training set, this has the effect of moving the embedding vectors around for each word until the model is successful at discriminating real words from noise words. Okay, so all we are going to do is we are going to have the real words, and we're going to fit the real words and compare with the distractors, random distractors or random noise, and tweak the embedding of the word such that the value of the loss is minimum is minimum overall, right? So that's basically the idea. At the beginning of training, the embeddings are simply chosen randomly, but during training, the backpropagation automatically moves the embedding around in a way that helps the neural network perform its task. Typically, this means similar words will gradually cluster close to one another and even end up organized in rather meaningful way. For example, embeddings might end up placed along the various axes that represents gender, singular, plural, adjectives, nouns, and so on. All right. So those are the you know human way of interpreting it, whether it's an adjective, whether it's gender, and so on. So basically, the neural network does not care about any of these attributes. It basically figures out the vectors, the numeric representation of each word based on where do they occur. All right, where do they occur? In what context each word is occurring? So, so, so it's basically a blind set of numbers. We don't know the meaning of each of these numbers. Okay, all we know is that two words having similar vectors, smaller distances, are going to be similar in nature. Similarly, if we subtract one from another, the new vector that comes would represent the the distance, and if that distance, if that delta is in some way similar to another, those vectors will be parallel. Okay, so here what we are trying to show is that king minus queen and man minus woman are the two vectors which are parallel. Since this is a vector as in a list of values in n-dimensional space, so we are subtracting king minus queen and man minus woman, and this way we are able to see that these two vectors have these two vectors, the delta vectors, have less cosine distance. What is the cosine distance? Anybody? What is the cosine distance? No idea? Okay. Euclidean distance and cosine distance are two different ones. Okay. All right. All right. So, okay, Binda says cross product. All right. Yes, you are close. Okay, you're close. Let me describe. I think this is something that we had briefly talked earlier. Yes. Yes, it is kind of projection. Thank you, Ross. Yes. So I'll just briefly describe what it means by cosine distance. Okay. So cosine distance between vectors. All right. Let me ask you. Yes. Thank you, James. That's exactly what it is. So it takes the angle into account as the measure of distance. Okay. What is cos of 90 degree? Not cost of 90 degree. It is 0, right? And the cos of 1, cos of 0, 1, right? So if you think about it, if there are two vectors at 90 degree, this is vector A, this is vector B. Okay, so the cos of the angle between them is 0. Okay, that means these two vectors are orthogonal, and therefore their cosine distance is very high. Okay, so the cosine, this angle is what it means. So the cosine distance represents that if the cosine, you can say cosine similarities, sorry, cosine similarity, not distance, similarity. Okay, so cosine similarity between the two vectors is basically based on the angle between them. So like A and B have nothing in similar, therefore is 0. Since A, and here in this case, let's say there is one vector in this direction, other is also in this direction. This is A and this is B. Then the angle between them is 0, and therefore they are similar. All right. Now, how do you generally find the cosine similarity? Okay, how do you find the cost of angle? Basically, the idea is to find the cos theta. Okay, this theta between the two vectors, right? So how do you find that? All right, so the way you do is A and B. So what we do is A dot B is generally equal to A modulus of A and mod of B, and then multiplied by cos of theta, right? So the cos of theta, if we just take it to the down of it, right, it'll become, so cos of theta equals A dot B divided by mod of A and mod of B. All right. So good, great. So basically, or you can say that the unit vector A dot unit vector B. Okay, that's what it means. So at any point of time, if you want to find out the cosine similarities between two values, you do a dot product between their unit vectors. All right. So, and how do you compute the unit vectors? Let's say, so if the word man and woman we want to compare, right? Let's say man and king, there is one word called man and there is another word called king. Okay, so here let's say this is represented as say 1.5 and zero point 0.5. Okay, we don't know the meaning of their columns, it's just some vector. Okay, so this is, let's say, 1.1, 0.4 and zero point 0.3. Okay, so we can simply, if we are in any of the notebooks, let me just open my usual notebook, then I can just show you. All right, let's say this idea will occur multiple times, and that's why I would like to go over it in a bit more details. All right, I'll just put it here somewhere, maybe. Okay, so let's say the man is np dot array, say 1.5.5, and the king is np dot array 1.4.4. Okay, so okay, so the how do you compute the absolute? I think, does it work? Okay, so np dot, does this work? No. No. This one. No. So we can just say man into man. Okay. And we could just say sum. And could say. All right. So this is how we can compute the mod. All right. And let's say, this is our unit vector. Okay. So man underscore u dot. All right. So they are very similar. They are very similar. Of course, this is wrong, and I'll have to change it. That's why the value was right. So this is very similar, you can see. Had it been, let's say, completely different, let's say these are two different vectors, then it could have been, they could have been almost like zero. They are really, really orthogonal. They are basically orthogonal. All right. So this is essentially the idea behind the dot product. Okay. To find the similarity or dissimilarities between the two things. Okay. So if we could represent something as a vector, we can find the cosine similarities by doing the dot product. All right. And how do you find this vector? By subtracting this from this. Okay. By just subtracting a minus b. All right. So this is what it means by the vector. So once we are able to represent each of the words in the vector format, we will be able to do a lot of magic. And how do we come up with these embedding? These embedding, let the system come up with. All we will do is we will aim for a loss function such that the word that was actually fitting should have the higher probability as compared to the distractors or as compared to the noise. So that's what we do as part of this representation. Okay, so where were we? Yeah. Okay, so at the very beginning of the training, the embeddings are simply randomly chosen. But during backpropagation, during training, the backpropagation or the gradient descent automatically moves the embedding around in a way that helps the neural network perform its task. Okay. Typically, this means that words will gradually cluster close to one another and even be organized in a rather meaningful way. For example, embedding may end up placed along various axes that represents gender, singular, plural, adjective, and so on. So this is basically the methodology behind it. So how to do it using TensorFlow? In TensorFlow, we first need to, okay, yeah, I'll post the code here. Why although it's not right now required, Why I wanted to show you is because the word cosine similarity will be thrown again and again. There are many measures of similarity. One of them is cosine. The other, it could be, say, Tanimoto coefficient. And there are like hundreds of such similarities. The words will be used a couple of times, but cosine similarities is the most often used. All right. And all it means is the dot product divided by the magnitude of both the vectors. And all right. Now, first of all, we will need to create the variable representing embedding. This is a random variable that we are creating. Here we are creating a random variable, okay, from some vocabulary size and embedding size. We are just creating the embedding. So we are creating an embedding of 150 size. Okay, so we are given a data set. We have certain data set, and now we are going to create embedding. Initially, we are choosing the size of the vector as 150, the embedding vector size, and here we are filling it with random numbers initially. We are filling it with the random numbers, and then okay. Now again, notice that this means total number of instances, as in rows. Total number of rows are vocabulary size. For each of the word, we are coming with 150 size vector. Okay, and the range is from -1 to 1. Okay, suppose we want to feed the sentence I drink milk to neural network. We should first pre-process the sentence and break it into the list of known words. Okay, this is an important part because this technique is what you will be using in many other circumstances. So you will take the sentence, you will break it into the list of known words. You may remove the unnecessary words or unnecessary characters, replace the unknown words by, say, U and K, put a square brackets around. And since we are not creating embedding for numbers, so we replace the numbers by num. If there are URLs, we replace URLs by URL. All right, and so on. So we basically replace unknown words, numbers, or something that is not there in the dictionary with the placeholders. So these are the markers which we are putting. Once we have list of known words, we can look up each word's integer identifier from 0 to 50,000, before 50,000. Say, for example, each of the word in the sentence is, first word is 72, second word is 3335 and 288. At this point, you will be, so what we can do is, instead of feeding I drink milk, we will feed these numeric values from the dictionary. So we'll represent this with a particular number, a single number, so that we don't have to feed this anywhere. So we are feeding the dictionary words. So their sequence orders we are putting here. Their sequence orders we are putting here, and at this point, so instead of I, we are saying that I is our first word, and drink is some other word from the dictionary, and so on. So instead of carrying the string around, we are carrying the location of the word in the dictionary, or in the vocabulary. A question from Binta is, why do we choose 150 for embedding size? Okay, good question. So here we had Here we had chosen 150 as embedding size. Okay, so basically it's an arbitrary number. If you choose a larger embedding size, it's going to take more time. It's like choosing the number of weights. Okay, choosing the number of weights. Okay, so you could try the smaller or you could try the bigger, and the results could vary. What do we mean by -1, 1 in this one? Here we are generating the random numbers between random decimal numbers between -1 and 1. Okay, that's what we are saying. And the size of the array, NP array that's going to be there, or TensorFlow array, TensorFlow tensor. This is basically a tensor uh, with number of rows as vocabulary size and embedding size as number of columns. Okay, great. So at this point, you are ready to feed this. Once we have, again, one more thing we are doing, instead of using I, drink, and milk, and we basically picking their sequence orders from the dictionary, so that a unique word is identified with a unique number from the dictionary. Okay, and of course we are not going to um, uh, do a decimal representation of these numbers. Okay, these are strictly integer numbers. These are just representing the index in the dictionary where they exist. All right, and okay, so at this point, we are ready to feed these words to the TensorFlow using placeholder and then apply embedding underscore lookup function to get the corresponding embedding. Okay, so TensorFlow provides a nice function called embedding lookup. Okay, so let's say you have a dictionary, containing embeddings. So we could ask this function to look up the values for the training inputs. These training inputs are our words that we are feeding. So those are the keys here in this embedding one. So initially we have assumed the embeddings to be of this size, and here this embedding lookup only looks up in this one. This is a vector of 2 dimension, and for each of the training inputs will be a list of numbers. List of, basically we will be converting every number that will feed here into something like this, and we will ask, we will, if we do not use this, then we'll have to write our own for loop that for training input I, go to the embedding, ith embedding, and then generate a new vector. So instead of we doing it, we are using the TensorFlow to do it for us. All right. So once our model has learned good words, it can actually be reused fairly efficiently in any NLP application. In fact, instead of training your own word embedding, we may want to download pre-trained word embedding, just like when reusing pre-trained layers, we can choose to freeze the pre-trained embeddings or let backpropagation tweak them for your application. All right. The first option will speed up training, but the second may lead to the slightly higher performance. Okay. So there are actually quite a few libraries available. I'll just show you, let's say glob vectors. One is Gensim. Okay. So Gensim word embeddings are quite useful. So you could use Gensim in your application and can pick up the result. Okay. Then similarly, we have glob vectors. Okay. So the glob vectors are also quite powerful when it comes to comes to the as in glob vectors are quite powerful when it comes to finding similarities. Okay, so you can take a look at this. Just the methodology of coming up with glob vectors is slightly different from the word2vec. Okay, and so you could use any of these. And sometimes when we don't want to get into so much of details, we may want to use TF-IDF, which is like very basic count of words. Okay, and all right. Those who are just looking for, if you're looking for the NLP library, you could use either Stanford NLP, okay, or you could use you could use Spacey, okay, and you could use, say, Blob Text, okay, so not Text Blob, or NLTK. All right, I'll just put it in the notebook so that. All right, so I'll just, where is the, here, I'm just putting NLTK and text blob. Okay, sure. Okay, so NLTK was a kind of grammar parsing. It is not really the way we are looking at the meaning of words right now. Uh, it would basically parse the language parser. And this one is essentially simplified NLTK. Okay, if you are just looking for natural language processing before we go further, so you could try this one. And Spacey is essentially built on top of the neural networks. It's actually quite fast, and Spacey is uh, right. Spacey is good, and Stanford NLP is a general purpose uh, one. Okay, so all right, it's a whole project under which there are. So all right, another term that will be thrown around often is NER. NER means natural, sorry, named named entity extraction. Okay, so this one also provides the grammar and let's say grammar. Okay, and NER. All right. Similarly, Spacey also does that, and you could take a look at these libraries. These are quite popular libraries, and Stanford NLP general purpose kind of a project, a large project, which has all kinds of libraries. Okay, so for sentiment analysis there is one, and for others there is one. Okay, so just if you are interested in going for if you're interested in natural language processing, you should take a look at those. All right, now we are specifically talking about how do you come up with something like something so robust as any of these. So the hardest part of these is essentially the coming up with coming up with word embedding. A question is, are these only for English? Not really. So most of these are for English, but there are some that are handling the other languages as well. Okay. All right. So you can right away start using those APIs based on just explore which one does what, and you will get a fair bit of idea. And that will be the right way of knowing NLP. And in our case, what we are trying to do is we are trying to do the machine learning on top of the embeddings. And since using that, we could do all kinds of predictions. This one is the most powerful way of doing any kind of predictions, right? Let's say you have a large website and you are trying to figure out that, let's say you are running things like Quora. Let's say you're running a website like Quora and you're trying to figure out that why certain questions have less number of answers, or certain questions are having not much of attraction as opposed to the other one. So what you do in these cases, right? So what you'll do is in these cases is you will basically convert all of the web pages into the word embedding and put that as every page will be every instance in your data set, whereby the content of the page would be represented by a series of the um, word embedding from the each page, and then you'll feed it to say either a neural network for the supervised learning, and you'll figure out that which pages why a particular page is having more hits as opposed to the other. For example, a word like sex, or word like say top n, those words might be giving more hits as compared to the other one. So the system will figure this out. So once we are able to convert a content or the text of a particular page uh, into numbers, then we can do the rest of the whatever we learned in this course. You can apply all of that on the text, right? So essentially the word embeddings are fairly useful and gives you the entire control of your uh, of your data set containing the text. All right. So in fact, instead of training our own word embedding, we may want to download pre-trained word embedding. Just like when reusing pre-trained layers, we can choose to freeze the pre-trained embedding or let backpropagation tweak them for your application. The first option will be okay. So just like when we did the pre-training, right? What we did in case of reusing pre-trained data, we could download any of the models from the internet and start from there. Instead of starting from the scratch, we could start from there, and we could basically, just like that, we could freeze some of the layers or some of the layers, and then let the backpropagation tweak for your application. All right, exactly like pre-trained models. So the first option will speed up training, but the second may lead to slightly higher performance. Say you are mostly working on financial application or biological application, so you may want to tweak the embedding a bit, or you may want to add the embedding a bit based on your text. All right. In those cases, this what we are learning now is quite useful. All right. All right. I'm going to go with the example in the notebook that will make more sense to you. All right. So I'm going to, all right. we are done with all of this. All right. Right. We'll start from here. Okay. Let's take a break for 10 minutes and back by break for 10 minutes. All right. So this section is based on TensorFlow's word2vec. You must take a look at this tutorial. It's actually really, really useful one. So it goes into more details the way we have discussed about things. And the things that we just discussed were basically based on this only. All right. So let's yeah. So there is a library called Gensim, which is basically built on top of Word2Vec. Even though the library Gensim is installed and I have copied one set of vectors here, but for now it is just too big for our lab because there might be other services that are running that are taking up the memory. And okay, so I think it is pulled only. It is don't you see it? Can you pull? You need to pull the script because I have updated a lot of notebooks. So I have already pushed it. And okay, let me close these. All right. So I've already done that. Okay, let's see if there is a new terminal and I could open. So going into ML, going into deep learning, and here I could say git pull. All right, so it is latest. And here there is, let's just see what is the difference. Notebooks are not super friendly with, okay. All right, not much of a difference, only this much. I could just say git commit, and I could say classwork, and I could say git push. All right, I've just made some changes, that's all. Great. So far, what we've learned is the overall mechanism of how would the embedding happen. Let's take a look at actually how would you how would you generate your own word embedding. All right. Let's say there's a text file. This text file is what we are going to use. It contains some amount of text, not too big text, but some good amount of text. So initially what we're going to do is we're going to download some create some folders, and then we'll fetch the data. We'll fetch the data and the it will return to us the data in that folder. Okay. So these are for downloading the data. And at this point, if you take a look, I'll just show you 20 words. Okay. So this text is basically is having this kind of content. Also, I can download this URL locally as well. Okay, and then it'll make more sense to you probably. Okay, so it's a 30 MB file. All right, let it finish. All right, why is it so super slow? Okay, so all it has is some text, and the initial lines, initial 20 words are anarchism originated as a term of abuse first used against early working class radicals, including the diggers of the English. Okay, and all right, so this way there are, all right. Now we will convert these words into some numbers. Okay, numbers as in the dictionary position. So we'll look up in the dictionary, and we'll look up in the dictionary here. So, and also we will put we are adding one more word in the dictionary called unique. Okay, here we are generating counters, as in we're counting the words. So we are finding the most common words, and here we are basically finding the unique words from that. And once we are done with that, we are finding their positions in the dictionary. We are finding their positions in the dictionary. That's all we are doing. Okay. So here, once we are done with it, we will have two lists. One is called words, and other is called data. Right? One is called words and other is called data. And let me just open the downloads, and okay, let me see what happens. All right. Yeah. Okay. So since the file is going to be bigger, I'm going to use tail with it. Tail, or let's say head, and say 200. That's our file that we have just downloaded. After this, we are going to go back to, right? Why is taking so much? It doesn't have a new line or what? Okay. So let's take a look at the text. Okay, looks like all of the file is loaded into the memory. How big is the file? 100 MB file it is. Okay, so this is the text. On the basis of this text, we are going to figure out the meaning of various words. Okay. All right, so that's our text. I can safely delete it. So here, all we have done is we have given them a number, all of these words, a number based on the dictionary. That's all we have done. So this is the data we have formed. This is what we are going to use in the in our neural network. Okay, so it's very simple. It basically, let's say, we first of all built something called a vocabulary. How did we build the vocabulary? By finding the unique words from the dictionary, from the whole corpus of text, all of the words. And once we have built the vocabulary, then we are finding each word in the vocabulary and putting and then we are giving it a number. So where in the vocabulary does the does a particular word exist? That's what is the vocabulary about. Okay, so that you can just browse around, take a look at this piece of code. All we have done is given number to the word. It is not embedding, it's just giving them sequential number. The a means, or a means 1, and ab- absolute means say 2, and so on. So that's what we have done. we have given, let's say, let's take a look at the vocabulary. All right, vocabulary. Oh, it did not execute. Okay, let's just execute it. Oh, this is going to be huge actually. Okay, so this one is basically going through the text and finding the unique word. You remember the word count example from our other sessions. So it has ordered the data based on the based on their frequencies and giving them sequential numbers. Say for example, the is most popular, so it has given 1 as the. Off is second most popular word, so it has given 2 to off. So it has created the ranks based on their frequencies. All right, that's what vocabulary. Vocabulary was the unique words from the text. Okay, what is enumerate? You can take a look at the example of enumerate. Enumerate here means when we, let's say here, when we enumerate, it gives us the index in the first tuple. Okay, so it gives you I, it's saying like for I in a list. Okay, so you get, this is the index and this is the actual value. Okay, so while we are enumerating, you are giving index as the first value. So that's what it is. All right, so great. We have just given put the enumerate there so that you can get the meaning of it. Otherwise, not really required. All right. Is everybody clear that what we have done? What does the data, when we say data and say 24, what does it mean? Okay. All right. Moving ahead. So a question from Binta is, what does it mean? It's just an example code. Just wanted to demonstrate what's the meaning of enumerate. That's why we have uh, put this part. Okay. Okay. And enumerate is gives us the list iterator, gives us the index of iteration. Okay. So that's what. All right, so great. We are able to do it. Now let's move ahead. Now this piece of code is little, how should I say? This is a little complex, whereby it gives us the batches from our text. Okay, so all it is going to give us the instances of data from the text. So it takes three things. One is batch size. Other is number of skips, how many window to skip, and how big is the skipping window. All right. So this generate batch is going to walk over our text and give us the batch sizes. All right. That's what it is going to do. It's going to give us the one is distractors as well as the context and the word. That's what it is going to give you. Let me just show you this. So here, let's say we are calling generate batch, and we are saying give us the batch of 20 size and the first batch. So when we call this here, we get we get the we get the we get the you see, we get the labels. These are the words that we're looking for, as well as these are the original words. Okay, so let me put it again. Okay, and so I wanted, let me go back here. All right. So what we have done is we have called this method getBatch. It is giving us the first set of words. Okay, first set of words. You can see the that's the these are this is our batch in, and the label here is these words. Okay, so S- these words. So all right. So the input data does not have the first word. Please notice that, while the label has the first word. So what we are saying is fit. This is the word that needs to be fitted into this text. Okay, and so on. So this is our input, and this is our output, expected output. Now, all right. So this is how we're going to figure out the embedding. What we are doing is we have created a function which will give us the instances and batch of instances actually. And what are the instances? Instances are context and the actual word. Context and the actual word. And that's what it has given us. So this is, okay, this is the whole, this one is our, all right, this is our batch. Okay, the originated is, let me just show you. Yeah, this is our instance from here to here, or you can say the whole batch. And for this whole batch, we have labels. Okay, let me just run it again, or let me call it with say 5 words, then it will make more sense to you. Okay, and labels. Okay, so for basically this is so here what we are trying to do is we are trying to create the context and the actual word kind of pairs. Okay, context and the actual word kind of pairs, and these numbers are nothing but the indexes of the word which we can find from the vocabulary. All right, so for each of the instances we have created, say, originated originated should fit in with the word called anarchism. Similarly, the originated, it should precede as, and the term should precede the ah. So that's what we have created. What we have done is we have created input and output just shifted by one, just shifted by one. So the when we feed originated, we should get the anarchism. That's the idea. So that those are the two words that are really closer. So that way we have created the batch and the labels, and so we'll call this function again and again on our data to generate batch, and it is going to give us one word and the next word as the label and the actual data. All right. Now let's move on to building the model. Now here we are saying that the batch size is 128. In each batch we are going to get 128 words. Embedding size, how big the embedding do we want? Here we are saying give me 128 size embedding. Then we are saying the skip window. How many window words to consider left and right? Okay, so how many times to reuse an input? okay, and so on. So basically, this is the way we are generating the tuples of context and the actual word. All right. Then the all right. So we pick a random here. We pick a random validation set to sample the nearest neighbor. Here we are going to here we this is right. Okay. All right. Actually, since I've zoomed in, that's why it wasn't clear. Okay. So yeah. So this is here we are basically the random set of words that we want to evaluate. That those are the random words, the distractor. So you could say the noise, and only pick only pick these many samples instead in the head of the distribution. So that's another part for the validation window and so on. So here is, and these are the valid examples that we are picking from this. Okay, so move ahead. So it's essentially setting up the initial variables. Now, so now is the next point. All right. This is sentence is wrong. So only pick um, probably this is what will be the word here? I think this is something else. Okay. All right. I really don't know what does it mean. No worries. So let's move ahead. So here we are specifying how many random words do we want to pick, right? Because if you remember that instead of checking against every other word, we are just picking the random words and checking against those whether the suggestions, whether the embedding that we have chosen are giving us the closer result or not. Okay. For the distractors or the noise, our embedding should give us wrong answer, while for the correct one, our embedding should give the right answer. Okay, so that's why we need the random distractors or noise. So moving ahead, so here creating the training labels, and this is the valid data set. Okay, so this is the input data. Next is we are creating something called initial embedding. Initial embedding is what we are feeding to the embedding variable, and this embedding variable is what we are going to tune. Just like weights, we are specifying the embeddings initially with random values. Okay, with random values. Then then we are creating the training inputs. So we know the training labels and training inputs. Now in the training inputs, so this is just like capital X. Okay. And here we are converting these training inputs into the numbers using the embedding lookup. Okay, using the embedding lookup. So we are going to find the embedding for these inputs. All right. Since since our training inputs are numbers of the same vocabulary size as this one, therefore this will give us, let's say, for a word like the, which is one, it's going to give us the first row, second row, okay, from this. All right. Did we run this part? All right. Now is the in the loss function. The loss function that we have is basically NCE loss function, the one that we discussed earlier. This is the loss function. For this, we need to feed the weights. We need to feed the weights, and the weights are generally basically it's a random number again in the beginning, and all right, yes, and NC biases are 0 initially. Afterwards, we are going to create the loss function and then create the Adam optimizer, feed the loss function to the Adam optimizer, and then feed the data to the training op. That's what we're going to do. So here also here we are computing the cosine similarities between mini batch examples and all the embeddings. So here we are computing that cosine similarities. How are we computing? By first of all computing the norm. Okay. And how do we compute the norm? By squaring each of the embedding, just like we did. And here once we do that, then we do the sum. And we are saying axis equals 1. That means go through the first axis and sum up all the values. Right? If you have two-dimensional matrix and you are computing the sum and you want to just compute either the columns or the rows, then we use the word like axis. Okay, so here we are computing the overall norm, and then we are dividing the embedding by the norm. So this is the normalized or unit vector of embeddings, and the then we look up for the valid embeddings using embedding lookup. Okay, and afterwards we are doing the matrix multiplication between the similarities of this normalized embedding as well as the valid embeddings. Okay, so this is let me just explain again. So this is the similarity that we are computing between the actual one and based on the predictions. Okay. All right. Once we have defined or created our model, then we can train it. Okay. Then we can create a session, and number of steps I have just reduced it to 500. When you have free time, just make it say 10,000. And here all we're going to do is the most important step in this is here. Okay. Here. So here what we are doing is we are basically running the session and passing the training off. And average loss is what we are computing over a period of time. Okay. This is just for printing purposes. All right. This is just for printing purpose. This is also just for printing purposes. Okay. The main work is this. Here, this is where we are running the session. So first of all, we generate the batch. We got the batch. Then we created the dictionary to feed the training inputs, the training labels from the generate batch. And once we are done with that, then we are feeding that here. We're feeding that here. Okay, so we're feeding that here, and training op and loss are the two things that we are calculating. Again, the average loss is just for display purpose, so we can actually remove everything else. So only thing that is remaining is the epoch, the steps, and getting the data from the batch, and then feeding our session, and we run the training op and the loss. So here, when we run the training op and the loss, it's going to minimize the loss, and loss is basically the NC loss, which checks the right against wrong. which checks, right, that you know already against the random values, and accordingly it is going to tweak our embeddings. Okay, it's going to tweak our embeddings. All right. A question from Bintao is, what is this? All right, I will explain. Actually, this is something that comes quite often. All right, so what does it mean here by underscore? Actually, underscore has many meanings. Okay, so when we say for a comma this, right, for a comma underscore from say 1 comma 2, I'll just say, okay, right? So it's going to ignore the second part, that's all. So if we have like something like this, and we are saying, so this is essentially for ignoring the second part. Okay, so we are ignoring the second variable. Underscore is essentially like choosing a variable and not using it. Okay, there are many meanings to the underscore actually. Okay, and in the usual sense, this is what it is. Sometimes underscore is also used with internationalization when you put the string like this. Okay, that's also used um, as with underscore, and sometimes this is underscore is also used in terms of say defining the private variable and so on. All right, so underscore is used to ignore here. Okay, so probably this is the one that you are. I think this is the one you're talking about, right? This essentially means that ignore the outcome of training up, only keep the outcome of loss. Okay, even if we put a variable here, it wouldn't harm, just that we don't want to waste memory for that variable. All right, so now let it run, and it's basically trying to figure out the values of embedding. Okay, so here the important part is, one is loss function. Loss function is something that is new here. It's NC loss, whereby we are passing the NC weights and biases and so on. And okay, so this similarity, we are doing it only for our display purposes. We're not using the similarity. Okay, we're only using for the optimization, we are only using the loss function here, and so on. Okay, so I think it is finished. All right, so we can save it either using TensorFlow. We could also create a saver, and using the saver.save, we could save the graph. Okay, here we are using the numpy save method, no particular reason. All right. Now we can plot this data that we have just generated on on a two-dimensional graph. But for doing that, we will have to convert our vectors into two-dimensional, right? Because our vectors have some 100 plus dimensions, right? Here, what was the dimension? 150, right? 150 is our dimension, so we'll have to convert that into lower dimension so that we could visually see what's going on there. Okay, so we are defining a function to plot with the labels, and then we are using something called distributed stochastic neighbor embedding. So this function is going to this function is going to this function is going to bring down the dimensionality to the number of components, which is 2. So it's going to use PCA, and it is going to convert our 150 dimension vector into two-dimensional vector. Okay, and then it is going to once it has applied this transformation, it is going to display all these labels on a graph. A question from Bintao is, what does it mean by assert? Okay, here. This is just for checking. Okay, just for making sure generally when you are writing your test cases, when you are writing your functions and you want to defend against an invalid value, you should just write assert. Okay, that's what it is. All right, so here we want to take a look at what our neural network has generated for us, and we should be able to visually see the words. Okay, so does it make sense to you? You can see China and Roman nearby, and film and religion nearby. Okay, all right. All right, so you can see this is the data that has been generated. Probably if we run it for 10,001, then these results will be far more similar, far more meaningful. All right. Right. So this way you can generate the word embeddings, and also you can take a look at, say, final embedding. How do they look? These are the final embedding that have been generated. Okay, so this is final embedding for, let's say, 0th element. These are 150 values representing one word. Okay, so let's take a look at, say, all right. What was that function that we used earlier? Vocabulary. All right, so here we have data and words. Data, let's say we use 5, and we say here words. Okay, So 0 to 5, these were the words, and and here, or should I take a look at more than 10 words? All right, used against. All right, I'm just trying to see if I could come up with some meaningful words. Okay. All right. So let's take a look at, say, the and ah. Okay, the and ah. 0, 1, 2, 3. 0, 1, 2, 3. Okay, so final embedding of 6. This is, let's say, ah. And this is G 1, 2, 3, 4, 5. 1, 2. Okay, 1, 2. Okay, so this is 2. All right. So if we have a and the, they both must have like very close value, right? And how did we compute the cosine similarities? Let me just go up to the top. This is how we calculated the cosine similarities. Cosine similarities. And I wanted to show you this part. Okay. Here, right? If we define, let's say we define cosine similarities. Is there a cosine similarity function? Not here, TNP. Oh, it's not there. It's not there in NP. NumPy cosine similarities. It's in the SciPy. Okay, so import SciPy. All right. So that's the similarity between A and the. And let's say English, right? English is 103. And here we are saying English equals. What is the value? Final embedding. Okay. All right. This is very strange. Is it 1? Oh, this is something really different. It's not right. Okay. I'm going to create my own function and then we'll see. Define, first of all, what was that? Unit vector. Unit vector of any1 is equal to a into a, that is np.sqrt And here we are saying sum of this. Okay. And divided by this. All right, so does it work? Unit vector of A. Yes. Okay, so now we say define cosine similarities between A and B. And what we return is A dot, okay, so unit vector of A dot unit vector of B. That's what it means. Okay, so now we can see the cosine distance between these two. Okay, so all right. So the cosine similarity between the and I is more than the and English, but I and English is slightly lesser than the and a. So that's what is the result of our embedding. Though it looks okay, but it should have been a little bit more, little bit better. That was my expectation. Probably we'll have to run it more number of iterations, then we'll get better results. All right. A question from, yeah, question from Bintao is related to perplexity. This one is probably a hyperparameter of the TSNE algorithm, which brings down the dimensionality to number of components. Okay, so probably if we take a look at scikit-learn manifold scikit-learn here, then it'll make sense to you. Okay, so you could take a look at the documentation. Here I have already mentioned the documentation above. If you go a bit above here, it, so TSNE is a tool to visualize high dimensional data. The way we did LDA, okay, we could use even LDA to do this. It converts similarities between data points to join probabilities and tries to minimize the Kullback labeler divergence between the joint probabilities of the low dimension. So in simple words, when we want to convert it into low dimensional, either we use the TSNE with PCA as the argument, or we could use LDA, the LDA that we had used already in case of scikit-learn. Also, we'll talk about today how to use neural networks to reduce dimensions. All right. Great. So we were able to train our own neural network in order to generate the word embedding. Word embeddings were generated based on knowing the context of the words and generating the vectors such that each of the word belongs to each of the word fits in the context in the dataset. That's how most of these word embeddings have been generated. All right. The next part that I want to discuss is the machine translation. All right. Machine translation is here. Machine translation is not complete because it's not feasible to complete it in this session. Machine translation itself is a big area of research. I'm just going to give you an overview and give you an idea that how does the machine translation work with recurrent neural network. Rest of it, I'll give you references with which you can go through and learn and go into details. It'll take some time for you to go over the machine translation manual. And this is something cutting edge, which is happening right now. Lots of people are working on it. And every now and then, a lot of research is coming out. So machine translation is basically translating from one language to another. Okay. It's also called NMT, natural machine translation, which is, sorry, neural machine translation. And it's a big area of research. If you take a look at, say, no, there is a page called sequence to sequence, which is neural machine translation tutorial. It is essentially NMT, and it goes through like multiple approaches here. Okay, it goes through multiple approaches here, and you should take a look at there. Now, so with word embeddings in place, word embeddings is a very, very important part in almost all of the machine learning systems. So we have almost all the tools we need to implement the machine translation system. Let's take a look at this. So what we need is a encoder decoder kind of a system. That's what we're going to talk about, and we'll show you a piece of code that with which you could generate the encoder decoder network for machine translation. All right. So again, I'll like to warn you that I'm going to go over the model as such. I may not be completing it end to end. All right. So this is something that if you are interested in going further, you could go through the sequence to sequence paper. That one is far more detailed. All right, let's take a look at simple machine learning model that will translate English sentences into French. Okay, so the important part is that this machine learning translation system is built of two neural networks. First one is taking the source language, and second one is taking the neural network or the weight, or you can say the outcome. The second network is taking the outcome of the previous network, along with a sentence in the French, and then is generating another sentence in the French. Okay, so basically the encoder decoder network for machine learning looks like this. We have here we are feeding the English language. Here we are feeding the Spanish. I think this is French. We're feeding French, and then here it's generating the translation. All right. And during the training time, we feed the input as well as here we are feeding the French twice. One we are feeding the actual translation as well as the source language, and here it's generating the results. We are making sure that the outcome of this one should be same as what we have input. All right. So for that, we'll be tweaking the weights and so on. All right. So let's learn how the encoder decoder network for machine learning translation is trained. Okay. The English sentences are fed into encoder, and the decoder outputs the French translation. Decoder outputs the French translation. All right. So there are two neural networks. Both are recurrent, and it's a composite of like two recurrent networks. One is encoder and other is decoder. So here note that the French translations are also used as inputs to the decoder, but pushed back by one step. Okay, by one step, what does it mean? We are just ignoring one of the words and putting end of the statement. So in other words, the decoder is given an input, the word that it should have output at the previous step, regardless of what it actually outputs at the current step. Okay, so it is basically we are giving it the input such that such that it should, whatever it should have taken in the previous step, we are giving it now. So the next step is what is generated by this. So this is our English sentence. This is our French one, uh, corresponding one, and then we are expecting certain result here. So there will be a difference, something like this, and for this we'll be tweaking various weights in the neural network so that the predictions are same as the target. All right. All right. So for the very first word, the decoder is given a token that represents the beginning of the sentence. The decoder is expected to end the sentence with EOS. So since we want to explicitly mark the end of the line as well as the beginning of the line or beginning of the sentence, we have the markers for them. All right. So that it can differentiate between where it ends and where it begins. All right. So here the question that is there, that why are the English sentences reversed before feeding to encoder? Because it's a recurrent network. So the one I is going to be fed in the last. Okay. The one that is going to be fed in the last. And this ensures that the beginning of English sentence will be fed last to the encoder, which is useful because that's generally the first thing the decoder needs to translate. Okay, so remember in the recurrent network, when we feed something at the last, that is the one that is having the highest influence, and hence this one will see the I first and then the rest. All right, that's why this is more optimum. This is more optimum than than the passing I milk drink. So reverse is far more optimum because here this will see this one, the last one, as first, because this one will be fed the last in the last step. So each word is initially represented by a simple integer. So each word, instead of feeding in the strings, we are feeding a corresponding index of the number, index in the dictionary or index in the vocabulary, you can say. Okay, this is just a simple identifier, like you have IDs in any SQL table or any Excel sheet. Next, an embedding lookup returns the word embedding. Okay, so here, as soon as we feed these words using embedding lookup, these words, these 288 and 72 and 335 will be converted into a vector of decimal numbers. Okay, that's the embedding. This is dense, fairly low dimensional vector. Okay, this is fairly low dimensional vector. These word embeddings are what it actually fetches to the encoder and the decoder. All right. At each step, the decoder outputs a score for each word in the output vocabulary. All right. And then the softmax layer turns these scores into probabilities. Okay. As usual, we are using the softmax layer to output the probabilities. And for example, at the first step, the word J may have probability 20%, 2 may have a probability of 1%, and so on. The word with the highest probability is the output. Okay. All right. So how can we use encoder-decoder network for machine translation at the inference time, since we will not have the target sentence to feed to the decoder? All right. So how can we use the encoder-decoder network for the machine translation at inference time? since we may not have target sentence to feed to the decoder. All right, so we may not have the target sentence to feed to the decoder while we are inferring the system. So we'll simply feed the decoder the word that it outputs at the previous step. Okay, this will require an embedding lookup that is not shown in the diagram. So basically, basically will feed the decoder the word that it outputs in the previous step. Okay, so that we don't have to. Okay, so if we don't have any sentence to feed, we will not feed anything. Instead, we'll just feed the output from the previous one, and so essentially this output is being fed twice. One is from this side, other is from this side. All right, so this is a very simple overview of how does it work. So in simple words, it's an encoder decoder network whereby we are feeding the languages from one side, and it is trying to come up with the it is trying to come up with the translation in terms of the vectors, and then we are doing again the vector lookups here to come up with the uh, target words. All right, so I think that vector lookup, okay, no, it doesn't give the vector lookup. Instead, it gives the probabilities here, and those probabilities, based on those probabilities, the vocabulary is picked. Okay, that vocabulary is picked. All right, so this is what it looks like. All right, so take a look at, let me just walk you through the basic one. It doesn't work as such, but you could make out the meaning of it. So first of all, we are defining the usual variables, the number of steps, number of neurons, and so on. And next is that we are defining the sentences. Here, these English sentences are these English sentences are basically fed as X. The French translation are French translated sentences are Y. And all right. Next is that we basically create an encoder inputs by unstacking, just like we did earlier for unrolling, and then we did transpose and so on. And then we are creating LSTM cells. We're creating LSTM cells. Again, it has the multiple layers of the LSTM cells. And then this is multiple layers of LSTM cells. And then we are basically converting the encoded inputs into the vector sequences. Okay, into the vector sequences using this lookup. All right, then we have logits that is going to okay. All right, yeah. So actually this one, this particular legacy sequence to sequence network is what is actually creating the network. So here we have created the cell. We are giving it cell inputs and the outputs and embedding size. So this one is the one which is creating the entire network, and it's giving us the logics, and by using the outputs we are creating the layer for logistic I mean the last layer, logistic layer, in which we have all the probabilities and so on. And finally, once we have reshaped everything, and then we are computing the cross entropy, computing the reduced mean, and then we are minimizing the losses. Now here at this point of time, you can create session and feed English and French sentences. All right, at this point of time, that's what it is. But this is a little bit tricky here because we need to load the sentences, convert them into numbers, and then we need to feed them. All right. So this is a generic overview. I would still say that go through the machine translation paper at TensorFlow, then you will get a bigger picture. This is just to give you an idea that creating a machine translation system is possible based on what we've learned so far. All right. So, all right. A question from Bintao is why n step minus one in this? So as we said that we are going to feed one lesser than the previous one. So here, as we are saying here, all right. So here, so this is the W, and note that the French translations are used as inputs to the decoder, but pushed by one one lesser step. All right, that's the only difference. A question from Bintao is, could you load some English sentence to try? I don't have right now the corpus, but I can try maybe at a later point of time. I'll be trying to create, this is something that is to be done. Maybe we'll have to find out the English sentences. The TED Talk, maybe we can download the TED Talk data and try. All right, that we will try later. All right. So this was an overview of the machine learning, machine translation using the neural network techniques. And the next step would, the next step would be that we get some sentences, try to feed into it, or we go through the sequence to sequence network in more detail, step by step, and see how it goes. All right. So you could give it a try, the sequence to sequence URL, and you'll get a little bit more details about how it goes. All right. So that's pretty much with respect to the machine translation. And I would like to start with the encoders, the autoencoders. All right. All right. Great. Let's move ahead. So far, what we have learned is that the machine learning, the neural network could be used only for supervised learning, but it's not so. Okay. So this is a very interesting idea here that you're going to learn, that the neural networks could be used for many other uses, right? So autoencoders are artificial neural networks capable of learning efficient representation of input data called coding without any supervision. The training set is unlabeled. These codings typically have a much lower dimension than the input data, making autoencoder useful for dimensionality reduction. All right. So let me just share the slides with you. All right. So the so basically autoencoders are capable of figuring out the coding between the data. And this is why autoencoders are used for dimensional reduction. I know that this doesn't make sense. When we talk more, you'll get an idea. So why use an autoencoder? Useful for dimensionality reduction. Autoencoders act as powerful feature detractors, and they can be used for unsupervised pre-training of deep neural network. Lastly, they are capable of randomly generating new data that looks very similar to the training data. This is called generative model. Say, for example, you want to generate new faces from existing faces, right? In that case, you can use autoencoders. All right. For example, you could train an encoder on pictures of faces and it will then be able to generate new faces. All right, using the input data. So we are adding some noise to the existing faces. Surprisingly, autoencoders work by simply learning to copy their inputs to their outputs. This may sound like a trivial task, but we will see that constraining the network in various ways can make it rather difficult. All right. So so basically the autoencoders are like usual neural network, maybe deep neural networks, and the input layer as well as output layer both are having the same data. So we are feeding input as well as output the same thing. Okay. Now at this point of time, you'll wonder like, what if it it makes all of the weights as 1 and biases at 0? That would lead the output as same as input, right? But it's not so. Okay. If we fine tune the number of neurons and we change the layers, decrease the layers in between, then you will notice that um, it will be retaining only the information which is most crucial to the data, and it'll basically shrink it and expand it. We'll go into more details. So autoencoders, you can limit the size of internal representation, or you can add noise to the input and train the network to recover the original input. These constraints prevent the autoencoders from trivially copying the inputs directly to the outputs, which forces it to learn efficient ways of representing data. In short, the codings are byproducts of the autoencoder's attempt to learn the identity function from under constraint. So though we are feeding the input and output the same thing, right? So in this neural network, the input data as well as output data is same thing. It needs to figure out the output from the same input data. But you can limit the size of the internal representation, or you can add a bit of noise to the input, and and this way it makes it a little difficult to recover the original data. If you have like lesser number of neurons in middle layer, or you have added more noise, then it becomes difficult for it to recover. And these constraints prevent the autoencoders from just copying the input to the output. All right. This which forces it to learn efficient ways of representing the data. In short, the codings are byproducts of autoencoders' attempt to learn the identity function under some circumstances. All right. So it's like learning to draw. We see the photo, we draw the same thing, and so on and so forth. And later on, that's how most of the artists learn to draw, by just looking at existing photos and trying to draw the same photos. And later on, that we can do later on the artist can create new paintings and so on. So, but the beginning is by just copying. In the same analogy is applying here, that autoencoders begin by just copying the input to the output, and slowly they learn the pattern. Slowly they learn the pattern which most of the images follow, or most of the data follows, and that's how. So autoencoders, what will it learn? We'll explain in more details how encoders work, what types of constraints can be imposed, and how to implement them using TensorFlow, whether it is for dimensionality reduction, feature extraction, unsupervised pre-training, or as generative models. All right, let's understand why constraining an autoencoder during training pushes it to discover and exploit pattern in the data. With an example, let me ask you a simple question. Which of the following sequences are, which of the following number sequences you find easiest to memorize? There are two sequences on the screen. Which of these you find it easy to memorize? First one is 40, 27, 25, and so on. Second one is 50, 25, 76, 38, 19. Which of these are easier to memorize? Okay. Bintao says short one. Take a look at it closely. Take a look at the bigger one closely. Do you see something interesting there? Can you notice anything? Kamal says the numbers are halved. Okay. So, all right. So 50 is halved. 50 is halved. Then this one is, I think this is how much? 3 times. Then halved. Then halved. Then 3 times plus 1. And then half and then half. All right. Correct. So, point from Kamal is that, so you remember if you keep halting till it becomes odd and so on. All right. Just look at it again. So here in the second one, there are two things happening. Two things happening. One, we are sometimes we are dividing by 2, and sometimes we are multiplying by 3 and adding 1 to it. All right. So at first glance, it may seem that the first sequence will be easier since it's much shorter. However, if you take a look at it closely, you'll find that the second one is essentially easier because in the second one there is a pattern. And what is that pattern? Pattern is that if the number is even, divide it by 2. If the number is odd, then multiply it by 3 and add by 1. Okay? Multiply it by 3 and add by 1. So there is a pattern. So if I know the initial number as 50, I can generate the rest of the sequence by this knowledge. While in the first case, it's very hard to memorize so many numbers, right? So this is a famous sequence known as Hillstone sequence. Once you notice this pattern, the second sequence becomes easier to memorize than the first one because you only need to memorize the two rules, the first number and the length of the sequence. Okay, that's the only two things that you need to know. Note that if you could quickly and easily memorize very long sequences, you would not care about the existence of a pattern. Okay, if your memory is really sharp, then you will quickly tend to memorize as opposed to trying to figure out the pattern in the data, right? So you would just learn every number by heart and that would be that, right? It is the fact that it is hard to memorize long sequences and that makes us recognize patterns. That makes us recognize patterns. And hopefully that clarifies why constraining an encoder during training pushes it to discover and exploit patterns in the data. All right. So the relationship between memory, perception, and pattern matching was famously studied by William Chase and Herbert Simon in the early 1970s. And so this study of chess player is similar to an encoder. They They observed that expert chess players were able to memorize the positions of all the pieces in the game by looking at the board for just 5 seconds. So expert chess players were able to memorize the entire chessboard by looking at for 5 seconds. And we those who are not expert at chess, we find it difficult to memorize it. However, this was only the case when the pieces were placed in realistic position. When pieces were placed in realistic position from the actual game, not when the pieces were placed randomly. Okay? If let's say if you swap the places of pawns to elephant and elephants to pawn and so on. So if you shuffle that like random one, they won't be able to memorize. Okay, so they were able to remember it because they saw the pattern. They saw that from the initial state, these are the steps that had led to the current state. And since this one is giving check to that one, and if I move this one there, and so on. So there's a pattern that a chess player saw. If there was no realistic position, then they won't be able to remember the board. All right. So chess players don't have much better memory than you and I. They just see chess patterns more easily thanks to their experience with the game. All right. So probably that gives us more peace of mind because they don't have bigger brain than us. They have the similar physical memories than as us. Just that they just see patterns more easily than us because they have their neural network is developed. They have some experience. Noticing pattern helps them store information efficiently. All right. So just like the chess player in this memory experiment, okay, an autoencoder looks at the inputs, converts them into an efficient internal representation, and then spits out something that looks very close to the inputs. Okay, so autoencoder consumes the input, then tries to reproduce the same thing from its memory, and that should look very close to the input. All right. So an encoder or recognition network that converts the inputs to an internal representation, it has two parts. One is called encoder and other is called decoder. Decoder is a generative network that converts the internal representation to the output. So inputs and the internal representation and the output. So generally the autoencoder is made up of two parts. An autoencoder typically has the same architecture as MLP, multi-layer perceptron, except that the number of neurons in the output layer must be equal to the number of inputs. Okay, here the number of neurons should be equal to the inputs. This is just one hidden layer composed of two neurons and one output layer composed of three neurons. So the outputs are often called the reconstruction since the autoencoder tries to reconstruct the inputs and the cost function contains the reconstruction. reconstruction loss that penalizes the model when the reconstruction are different from input. Okay, so the cost here is compare this with the original. If they are same, then the loss is low. If they are different, then the loss is high and it penalizes it. Okay, because the internal representation has lower dimensionality than the input data, it's 2D instead of 3D. So here, whatever was the data was converted into this stage, right? Which means there's going to be a loss in the data, and then this is getting converted. So it is like resizing and keeping on resizing an image to a very low size, and then again resizing it up. So there would be a loss of pixels. Okay, there will be a loss of pixels. All right. So an undercomplete autoencoder cannot trivially copy its inputs to the codings, yet it must find a way to copy to it must find an output, a way to create an output similar to the input. It is forced to learn the most important features. So since it cannot retain everything, here we are constraining it. It cannot retain everything. So here, because of the backpropagation, it will only retain the important features from the input. Okay, so the backpropagation will, since we have to minimize the loss function by comparing the input and output, so we have to minimize that loss function. So the backpropagation is going to force it to only learn the important characteristics of the input data. So let's implement a very simple undercomplete autoencoder for dimensionality reduction. All right. So if the All right. If the autoencoder uses only linear activations and the cost function is the mean squared error, then it can be shown that it ends up performing principal component analysis. Now we'll build a simple linear autoencoder to perform PCA on 3D dataset, projecting it to 2D. Okay. So here is some data. Let me try to show you that how to convert a 3D data into two-dimensional one using autoencoder. Okay, so okay, first of all, we are defining the usual functions. Then we are here. So here we are generating a three-dimensional data. This is some data that we are generating. Okay. So this is three-dimensional data. So you can see each record has 3 X, Y, and Z. Okay. And here we are importing standard scalar. So we are scaling our data to fit. Now let's build the autoencoder. So you can see that there's nothing much to it. We are importing TensorFlow, resetting the graph. We are defining number of input features. And we're defining the number of hidden layer. All right. Okay. So these are the number of input features. Then we have number of neurons in the input middle layer, and then here the number of outputs and the learning rate. So number of outputs and number of inputs is same. number of input features and output features is same. And here, as you can see, we are creating the input placeholder. Then we are creating a dense layer. So you can see tf.layers.dense. It is same as the fully connected neural network with these many neurons. And we are creating the output with this as the input with these number of neurons. Okay. So this is our reconstruction loss. Here we are saying tf.reduce mean, and we are subtracting output minus input. And then we squaring it, and then we are computing the mean of it. So this is our reconstruction loss. This is something that we are going to minimize. Okay, so we define our optimizer, create our optimizer, and then minimize the reconstruction loss using the optimizer and initialize the global variables. Afterwards, we are basically creating a session. Okay, the number of iteration and creating a session here, and then we are feeding the input data to our training op, which is this one. We are feeding the input data, and then we are evaluating the codings as well. Codings is what? The middle layer. Okay, the coding that we had defined earlier. Did we define coding here? Okay, I think we have not defined. Yeah, coding is the hidden layer. Yeah, you can see coding is the hidden layer, and that's all. So let's get started here. So we were able to take a look at our data, which is three-dimensional, and okay. So it has started training here. Okay, did it finish? Yes. So you can see now when we say coding well, this is the coding. This is the two-dimensional learnings. Okay. And if we plot the codings, then it'll basically look like this. Okay. All right. So what we did here was, this is our two-dimensional data. This is our two-dimensional data, and we converted the three-dimensional input to the two-dimensional data. So the hidden layer, the middle layer that we talked about, that's the one which contains the two-dimensional data from our three-dimensional input. All right. So since it was trying to minimize the uh, loss, it was trying to minimize the reconstruction loss. Therefore, it came up with the data or projections of the data in those two dimensions, which actually represent our actual data. Right. So that's pretty much with respect to the autoencoders. All right. This is pretty much with respect to autoencoders, and we can briefly start with the reinforcement learning, and then we can uh, go over the reinforcement learning in the next session probably. Okay, so let's so basically using so that's pretty much with an autoencoder. So as a finishing line, all I have to say is that by using our existing knowledge of neural network, we can do magics. Autoencoder is one such magic, and the next one that we're going to learn is the reinforcement learning. That's another magic. So by composing the neural network from one way or the another, we could do many things. All right. All right. So, all right. So I'm going to I'm going to just give you a brief introduction of reinforcement learning, and we will continue from the reinforcement learning next in the next session. I'm just going to go over a brief introduction. It's a very interesting exercise, and we should give it a shot. And this is going to be quite useful to you. All right. Okay. I'm going to say anyone can access it. All right. So should we start? All right. So reinforcement learning is something that we started the session with. The session was started with Mario game, and we're going to end with a similar example. We're going to end the course with a similar example, but we'll do that probably in the next session. All right, we'll just go over the basics, and we will try the first approach, and then we'll try the second approach in the next session. All right, great, great. So far we have learned quite a few things, and reinforcement learning is another application of whatever we learned. There are some more concepts that we will talk about. So reinforcement learning has been around since 1950s and produced many interesting applications over the years, like TD Gammon, a backgammon chess player, which was able to play this backgammon game. In 2013, the researchers from an English startup DeepMind demonstrated a system that could learn to play just about any Atari game from scratch and which outperformed human. It used only raw pixels as input without any prior knowledge of rules of the game. This is the one that we're talking about. This is the one, that Mario game that we demonstrated to you. So in March 2016, their system AlphaGo defeated the world champion, there as in Google's system called AlphaGo, defeated the world champion of a game called Go. And this was impossible. This was impossible earlier, but with reinforcement learning, which is essentially neural network with minor tweaks, we were able to achieve this. In this chapter, we will learn about what reinforcement learning is and what it is good at. So it is good at learning to optimize reward. So we are going to learn in more detail. So what we're going to do is we're going to make our bot that will play a game. All right. So reinforcement learning is learning to optimize rewards. In reinforcement learning, a software agent makes observations and takes actions within an environment. And in turn, it receives rewards. So our agent is in an environment, it takes an action, it gets the reward or the punishment. All right, negative reward is punishment. So it takes the actions within the environment and then it receives the rewards. So it gets the observation, as in the whole environment is an observation, and it takes an action, then it gets a reward. So the goal is to learn how to take actions in order to maximize the rewards. In short, the agent acts in the environment and learns by trial and error to maximize the reward. So how can we apply this in real life applications? Say, for example, a walking robot. Walking robot is nothing but it takes the countermeasures as it walks. For example, this is a very bigger example. For example, there could be a robot which is trying to balance itself on two wheels. As it starts falling forward, it'll move to the forward. If it starts falling backward, it'll move to the backward, and that's how it would balance itself. That's the most primitive version of a robot, and those are the Lego robot. You can take a look at those. So, so it's a walking robot, which is essentially a bundle of wires and having multiple layers of neurons. And it's all it's doing is based on the camera and sensors, it's observing the environment and taking the action accordingly. All right. So, so agent is here the program controlling the walking robot. The environment is the real world. The agent observes the environment through a set of sensors such as cameras and touch sensors, and it the actions it takes is by sending signals to activate motors. It may be programmed to get positive rewards whenever it approaches the target destination and negative rewards when it wastes time, goes in the wrong direction, or falls down. All right. So, so sometimes the punishment or the reward, negative reward, is when it wastes time or taking too much time or goes in the wrong direction or is falling down. Say, let's take a case of, say, Pac-Man, right? So the agent program controlling Pac-Man. The environment is the simulation of the Atari game. Action is 9 possible joystick positions. Observation is the screenshot, and the reward is game points. Okay. So actions, observations, and rewards. All right. Again, the other example of real life reinforcement learning could be the thermostat from Nest. And in this, the agent does not have to control a physically or moving thing, or physically moving thing or virtually moving thing. There's nothing to move, right? Okay. So agent is the thermostat. The rewards is positive rewards when agent is close to the target temperature. And negative rewards is when human needs to tweak the temperature manually. That's negative rewards. And agent must learn to anticipate human needs. So that's the overall objective by this reward and the reward and punishment way. There could be a system called AutoTrader, which keeps on looking at the stock market. That's the observation, and and then decides how much to buy and sell. The rewards is the monetary gain, and the negative reward is the losses. Okay, so there are many such examples, such as self-driving car, placing ads on a web page, or controlling where an image classification system should focus its attention, and so on. So there are many such systems in which there is a continuous input and continuous actions. All right. So there may not be any positive reward at all. For example, the agent may move around in a maze, getting a negative reward at every time step. So it's better to find the exit as quickly as possible. So here, there is no positive reward. It's only the negative reward at every step. Okay, the more time it spends, the more time or more number of steps it takes, the more negative reward it will get. Okay. So sometimes because of such kind of scenarios, what happens is the agent might pause thinking that in case I take a step, I'm going to anyway, it's going to reduce the values. So sometimes at these points when the agent is not able to take an action, it keeps on getting stuck or stopped. And sometimes it's smart enough to pause the game when it's not able to figure out there is a positive way of getting rewards. All right, those are the things that we will tweak and we'll learn how to tweak those. All right, next thing is the policy search. Now, algorithms used by software agent to determine its actions is called policies, or the algorithm that is used by software agent to determine its action is called policy. Policy is basically the main strategy. So the policy could be a neural network taking observations as inputs and outputting the actions to take. So it is the policy that is inside the mind of the agent, which will take the observation and take the actions. The policy can be any algorithm we can think of. It does not have to be deterministic. For example, consider a robotic vacuum cleaner. Its reward is the amount of dust it picks up in 30 minutes. Its policy could be to move forward with some probability p every second, or randomly rotate left or right with some other probability. The rotation angle would be a random angle between, say, -r and +r. Since the policy involves some randomness, it is called stochastic policy. All right. So the robot will have an erratic trajectory which guarantees that it can get to another place it can reach and pick up all the dust. Question is, how much dust will it pick up in 30 minutes? All right. So how would you train such a robot? All right. Let me just see. Okay. All right. All right. So how would you train such a robot? There are just two policy parameters which can tweak: the probability and the angle range R. Okay. Or do you guys want to continue from here in the next session? We are anyway going to have next session. All right. So we'll continue from how would you train such a robot. So all we are going to do in the next session is we are going to build one bot that is going to play one particular game, and we will optimize its performance. First, we'll start with a very basic policy. Then we'll improve the policy. Then we'll apply neural network, and then we'll make tweaks to it. All right. So we'll continue from here in the next session. All right. So thank you, everyone. I look forward to see you next Saturday. Bye-bye. Have a good day. Thank you, Balaji. All right. So the next session is going to be very interesting, more hands-on, and we're going to focus on making this strategy. All right. Bye-bye. Have a good day.